This is section 4.7, optimization problems. Let's check what we can do. First of all, let's talk a little bit about optimization. Optimization plays a role in a wide range of disciplines, including physical science, economy, biology, and we can probably list more real-life situation, real-life application. For instance, we quite often looking to maximize or minimize a few things. For instance, maximize profit, minimize cost. That's what we are interested at. Or we can say maximizing like areas, volume, yeah, in order to gain some other profits. Or maybe minimizing distance, minimizing time in order to be more efficient. So we can see to find the optimal solution means that we're looking for the best solution, yeah, in the given scenario. And for instance, we can see, this is graph from our textbook, scientists have studied how migrating birds choose an optimal velocity that maximize the distance they can travel without stopping, given the energy that can be stored as a body fat. Yeah? And we can see that's the graph, and it kind of like showing that the maximum, like about 11 meters per second, that's the maximum. They will, with that velocity, they will maximize the distance, yeah, to travel. Even the birds, they know the optimization problems. Okay, in general, what we have to do, we have to find maximum or minimum value of the function. Okay. Oh, I typed lots of information. You may pause the video or you may look at the slides, but let's just go through this. I mean, first of all, in these problems, we will have like situation, scenario. We have to find out a function. Yeah, we have to find the objective functions. And then, yeah, as mentioned, we have to find minimum, maximum. We will also describe the domain, like what set of numbers we looking at, what set of numbers make sense. That's we will have the domain. And if the domain is the closed interval, we will try to find the maximum or minimum value, the extreme value on the closed interval. And we remember we went through this process. We have to find the values at the endpoints. We have to find the critical numbers and the values of the function at the critical points and choose the highest or the lowest, depends what we're looking for. So that's the closed interval. On the open interval, first of all, we may not have guarantee that we may get this, like the maximum or minimum exists. Okay? That's first of all. But if the minimum or maximum exists, it must happen at the critical point. Yeah? It looks like we always have to find the critical points. And also, having a critical point and proving through the first derivative test or second derivative test that is minimum maximum, we still have to double check the end behavior. We have to look how function behaves at the endpoints. And for instance, if we found out local minimum value, yeah, like let's say we have a function local minimum and then function at infinity goes to the infinity, then yes, we will say this is the lowest point. And that means that's what we have to check. We have to make sure that we definitely found extreme values. Okay, let's put everything in action. This is a couple of steps, yeah, a short guidelines, which probably we always see similar steps. We have to read the problem, understand the problem, draw a diagram, always label the diagram because the labeling, the notation will help us to build a function. We have to identify what is given, what is required, and then determine if we maximizing or minimizing our function. find the function, find the relation between the given and required information, state the domain, okay, and then if we have the function, we have the domain, if we know that we're looking for minimum, maximum, we will try to find critical points. And if the domain is the closed interval, we will use the extreme value theorem. We will check the endpoints and the value at the critical points, determine extreme values. If it's the open interval, we will check the end behavior. Okay, let's see what we have. First derivative test. Okay, the first question is, a farmer has 24 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, we have a couple of things given, couple of things required. First of all, I will ask you, are we looking for the maximum or minimum value? And we may notice the last sentence, the last is the question and is asking what are the dimensions. We're looking for the dimension of the field, x times y, for instance, that will give us the largest area. That means the area will be our function, and we have to maximize, we have to find the maximum area, maximum, the dimension that will give us maximum area. Okay, and I do have a graph, so you can see. Yes, we don't know how. We have the river, and for instance, we can get 100, 20, 200, and 100. Yeah, that's 2,400 feet of fencing. But we have to think if that area is actually, if we maximize using actually these dimensions, or maybe 1,000, 400,000. Maybe this area is the largest. Maybe this one, 700, 1,700. We don't know. That's what we will do. We will just draw something like this, general, okay? We will name it X, Y, and the area, and we will work with this. Okay, that's what we have. We have this. Yeah, I just copy. Given information is parameter, but it's not exactly 2x plus 2y, it's 2x and 1y, yeah, because we do not need a fence along the river. That means 2,400 can be replaced in our notation as a 2x plus y. Okay? 2x plus y is 2,400. Now, we're looking for the area to be maximum, maximize. The formula for the area is x times y. Yeah, that means this is our function. We definitely at this point need a function of one variable. We will try to use the given information to rewrite, for instance, y in terms of x. Yeah. I mean, as we know, 2,400 feet is 2 x's and 1 y. And solving this equation for y, we can get 2,400 minus 2x. We did manage to get the x expression for y. Y is, we can rewrite y in terms of x. Let's take this 2,400 minus 2x and substitute to our formula. And maybe I can distribute 2,400x, 2x times x to x squared. This is the function that we have to maximize. Okay, and we may notice we do have a certain restriction, because quantity y, which is defined as a 2,400 minus 2x, must be always positive, because x and y is positive. Yeah, I can write this, x and y is always positive. So we can see x cannot be greater than 1,200. Okay, I will write this. So we have the restriction. Okay, but what we will do, let's first of all, let's find the critical point of this function, because we definitely need critical point. Critical point is the point where derivative of the function is 0. Because derivative is always defined for all of the x's from the domain, then we do not have the situation that derivative is undefined. Derivative defined, and derivative must be 0. That's the critical points. Let's see. Derivative is equal to 2400 minus 4x. Derivative is 0 if 2400 minus 4x is 0. And then x is, oh, I didn't solve it. Oh, okay, now I have the domain. That's what I was looking for. Oh, okay. So we can see domain negative 2x is greater than this. And when we divide by negative 2, x, as I mentioned, x is actually less than 1200 and always positive. Okay? So in what we have, we do have an open interval. X belongs to the interval. Yeah, x can only take the numbers between 0, of course, positive, and no greater than 1200, not even equal to 1200. Because if x is 1200, then we will have no fence, no like fencing will be left for y. We definitely need rectangle. Okay, that's an open interval. And also we may notice function, okay, our function, yeah, let's do one more thing before we finish our critical point. Our function has the quadratic, yes, quadratic form, negative leading coefficient. Then if we will picture the graph, it's parabola open down, yes, parabola open down. Then as function goes to like negative values, yes, negative infinity. Of course, we will have no negative values because we not consider, but if we will find this critical point, yeah, this is definitely guaranteed that is maximum. Yeah? We, of course, we not, normally I will say function goes to the negative infinity, but we will stop because we only consider positive x's, positive y's, positive area, of course. But the point is that critical point definitely will be maximum. We can even do the first derivative test. However, all of the other values are below this. That means this is the guarantee on that open interval that the end behavior, the points are lower than that critical point. Okay, let's finish 2400 minus 4x. If we solve for x, I believe is 600. Okay, that's when x is 600, that's the critical point. And we can say if x is 600, that area is maximum, but we still have to prove it. Let's put 600. Let's take the derivative and let's test the sign of the derivative. Derivative, I can possibly use different color, maybe this one is good. When we substitute like number greater than 600, like for instance, 700, maybe 1000, 4 times 1000, 4000, minus, yeah, 2400 minus 4000 will give us negative number. That means this is negative. And when I substitute like 1, for instance, number less than 600, 2400 minus 4 times 1, it's positive. Okay, that's we can see what's happened. Function is increasing, decreasing, local maximum. But we know, we check based on this end behavior of the function a and open interval. This is the absolute, I mean, this is the absolutely highest point. This is the maximum. That means when x is 600, the area will be maximum, but we need also dimension. Let's compute y. Y was defined as a 2400 minus 2 times x. X is 600. 12, actually it will be 12, right? 1200 if I am right. Okay, 600, that means this is 600, 600, and 1200. And the total is 24. So when we have this dimension, the area is maximum. We solve first optimization problem. Let's keep moving. Another one. An open rectangular box with a square base is to be made from 48 square feet of material. What dimensions will result in the box with the largest possible volume? We will maximize, because of the largest, because of that descriptive word, we will maximize volume of the box. And given information is 48 square feet. That's all of the material that we can use to build that box. Surface area. Okay, given, required. That's the box. I can label X, X, and H. It's open. We do not have a top. We don't need a material on the top, okay? But we definitely need material here, which is X squared. And we have 4 sides, the same sides. Doesn't look like they are the same, but all of the walls, the back, the front, the area is X times H, length times width, which we have 4 of those. Okay, let's try. Surface area. X squared plus 4, all of the walls, 4 times XH. That's given information. And we will, of course, say that this equals to 48. Yeah, we have some relation between XY, I mean XH and that 48. Okay, required volume. We have to find the maximum volume. Actually, we're not looking for the maximum volume, but we're looking for the dimension, which, having dimensions X and H, we can easily compute the volume, because the formula for the volume, which we need this, is the area of the base times the height, X squared times H. The same procedure. Yeah, you probably notice I have function V, X squared times H, but I have to get a function in terms of one variable. I will try to rewrite H in terms of X using the given information. That's the given statement. I mean, we figure out that formula. Given was only 48. And we can easily solve for H, subtracting X squared and dividing by 4X. Okay. I will put this instead of H, 48 minus X squared over 4X. We can simplify. Okay, now I have my domain, because we can simplify this, but okay, we can come back. We will figure out a little bit simpler, more simple form of the volume, but let's see where we are. Domain, the same thing. This is like, that's the length. X and H is definitely positive. Okay, that means X and H is definitely greater than 0. But looking at the given information, 48 is giving us some constraints. That means X is definitely positive. That's why we not worry for the denominator, but numerator must be positive also. Correct? 48 minus X squared must be positive, greater than 0. Let's solve this quadratic inequality. I did factor out, and I have the answer, but let's do on the side. We can see we will have 2 zeros. Okay, square root of 48, actually negative and positive. And when we test, because we're looking for this product to be greater than 0, we have to like test it. When I substitute the number, like big number, like let's say 100, we will have 100 negative, positive, it will be negative. Then this will give us positive and negative. Or if we prefer to look at this form, because it's quadratic function, I'm just talking about, it's nothing to do with the function that we will maximize, but just for this inequality to get the domain, 48 minus X squared looks like this. Yeah, it's parabola, open, down, 48 is Y-intercept, and yeah, And between these points, parabola is above, positive. And we can even cut this because we're not looking, we can't accept negative numbers. We can only accept positive numbers. It means from 0 to positive square root of 48. And that's what I type it. That's the answer. That's where we only these numbers and the same endpoints, because x cannot be 0, that will be weird, 0 length, and x cannot be square root of 48 because then numerator will be 0, h will be 0. Okay, I can erase this. So we still have open interval, but let's look at our function now, volume, the function that we maximizing. I cancel out that x, and yes, and I can possibly multiply 48 times x and x squared. That means we will have 48x minus x cubed. Okay. And what we see now it's not quadratic. Our function that we're trying to find the maximum, the absolute maximum, it's the cubic function x cubed negative. When we will think about the end behavior or the limit at infinity, yeah, if we like to write this as a limit, we know that looking at the limits at infinity for this expression, we're looking at the leading term, and the leading term is negative x cubed. Big numbers cube will be even bigger, and minus, it will give us negative number. That means as x becomes really big, the volume, which is that formula, I can put x, it will actually go to the negative infinity. We not, of course, consider that, but it will go down. Then if we found the local maximum, this will be the absolute maximum because all of the other values are below. Okay, so that's the proof on the open interval. Okay, let's take this function and find critical point and find tested critical point for maximum, minimum. Hopefully it will be maximum. Let's actually see how we can find derivative. Actually 4, it's like 1/4. That means 1/4, we can keep it on the side and we can just differentiate 48x minus x cubed. Yeah? Derivative of 48, x is 48, derivative of x cubed is 3x squared. Okay, I can remove this, and 4 in the denominator is just 1/4. Yeah, that means 1/4 is a constant. We don't need to use any quotient rule. No. Okay, derivative is defined everywhere for all of the x's from the domain. Then the critical number will be the value where derivative is 0. Derivative is 0 if this fraction is 0. This fraction is 0 if the numerator is 0. 48 minus 3x squared equals to 0. Let's solve dividing by 3, we get 16. Positive and negative 4, but we're not looking at negative numbers. X equals to 4 is a critical point. Let's test it. 4, we will test the sign of the derivative. I believe this is a good form of the derivative, v prime. If I substitute huge number, we know what's happened, negative, right? Values, we even have this negative infinity. If we substitute like number less than 4, 1, 2, 3, it will be positive. Then volume, our function behaves like this, increasing, decreasing, definitely local maximum. And this is absolute maximum because none of the values are higher. All of the values goes down, and this indicates that goes down. Okay, x was the length of the side, x, and we need also h. H is defined as a 48 minus x squared, 16, 4 times 4, 16. 48 minus 16 is 32. 32 divided by 16 is 2. 4 by 4, because we're looking for dimensions, 4 by 4 by 2. Quite low, right? Quite like not really tall box. We can see this box will give us maximum volume if we have only 48 square feet of material to build. Okay, nice optimization problems. Maybe one more, and then you can try to follow the same procedure. You may notice, you may rewatch this session. It's the same procedure, and we can take any question and do all of these steps. What I have? Oh, I have this question. I was thinking about the distance. Okay, let's do this one and let's do one more, the distance, okay? Then we will have two. A piece of wire of a length L is bent into the shape of a rectangle. Perfect picture. Which dimensions produce the rectangle of the maximum area? Again, maximum. Okay, I wanted something minimum. Okay, maximum area. The same thing. Oh, and I don't have the solution typed, which is even better. Okay, given information is L. And L, yeah, we can see that it's the length of the wire. But what we're doing with L, we're bending this and building the shape of the rectangle. Parameter will be 2x and 2y. And we have to remember L is given because L could be, I don't know, 50 like centimeters, 100 centimeters, maybe 5 centimeters. L is given, this is given. X and Y are the variable because we don't know what is X and Y to maximize that area. Yeah? The required information is area to be maximized. To be maximized. Formula for the area, and that's our function is X times Y, the area of the rectangle. And we will need, we have to solve this equation because we will need the area in terms of X. I need Y in terms of X. Shall we write this a little bit higher? Given information is the length of the wire, and this is 2x plus 2y. And solving for y, it will be 2L minus 2x, L minus 2x, L minus 2x divided by 2. Perfect. Let's take this L minus 2x, divide by 2. Let's multiply this by x. 2 is like 1/2. Yeah? 1/2, and then L times x minus x times 2x, 2x. Actually, let's multiply by that 1/2. 1/2 L. Yeah, I'm distributing that half because I saw 2x. L over 2x minus half times 2x is, oh, I lost something. X times, it's x squared, x squared. Okay, now the function looks better. X times L is Lx, x times 2x is 2x squared, 2x squared, okay? And half, but then I decided to multiply because 1/2 times 2 is 1. And I think it's a little bit easier. Okay, what restriction we have? X and Y are definitely positive. That means looking at this restriction L minus 2x, L minus 2x, that will be the domain, must be greater than 0, must be also positive because X and Y is positive and we have definition of Y. Then when I solve this for X minus L and divide by 2, negative 2, it will be negative over negative. X must be less than half of the L and still positive. And again, open interval. X belongs to the interval half of the L. X cannot be greater than half of the L. Because if this will be half of the L, it will be no wire left to build the width. Yeah? of course. Okay, that's we have open interval. The critical point will give us hopefully maximum. But we can see again, it's nice. The area is defined as a quadratic function. Yeah, let's do the quick analysis. Negative coefficient. Then this quadratic function, I can even draw it here. It will be parabola open down. I mean, this is critical point, definitely local maximum that we're going to find out. It will be absolute maximum because all of the other values go down. We stopped at positive numbers, but definitely behavior at infinity, at huge numbers, x huge numbers, the area, it's all of the values are lower than this one. Okay, let's find out. We need the derivative because we need a critical point. Derivative of L over 2x is L over 2. Derivative of 2x, derivative of x squared is 2x negative. Okay, and derivative is 0 if this is 0. L over 2 equals to 0. Negative 2x equals to negative L over 2. L over 4, a quarter of the length of that wire will give us maximum. Let's double check that is maximum. L over 4. I will test the sign of the derivative because sign of the derivative is telling us a lot. If we substitute, like for instance, L over 2 minus 2L, it's negative. And when we substitute, for instance, small number, almost 0, it will be positive because 2 times 0. And then function, the area is the function, behaves as increasing, decreasing. This is local maximum, but this is also absolute maximum because we know that other values are lower. Okay, it means the x is a quarter, that's L. A quarter of the L, and this will give us maximum L over 4. If x is L over 4, what is y? Because we need the dimension. Y will be, let's substitute, let's do in our head, 2 times a quarter will be half. L minus half of the L is half of the L. Dividing by 2 is also a quarter, L over 4. What shape we've got to maximize the area? We've got square because the length x and the width y are the same. Yeah. Okay, to maximize the area, we create a square. Nice question. With this parameter L, yeah, we don't like it if we don't have like the exact values, but yeah, that's nice question. And let's do one more, and then everything is yours. You can do your assignments. Okay, yes, you can look at this solution. I was typing a quarter of the L. Yes, let's do this one. Find the point on the line y equals to 4x minus 7 that is closest to the origin. Closest. Finally, we have to minimize a distance because we're looking for the distance from the origin to the point on the line. Okay, oh, that's the line given because that's the only information that is given, and the distance is minimum. Oh, I don't know if I think I type it. We can draw this line. This line looks like this. This is 7. This is negative 7 over 4. And we're looking for the point somewhere here. I don't know, x, y, the shortest distance to the origin. This green distance must be the smallest, yeah, the closest point. X and y. And we can see if we, because domain actually are all of the numbers. Domain like x and y could be all of the real numbers. X, but all of the other values will give us, like, if x is getting bigger, the situation at infinity, the values are bigger. That's when we will find, based on the critical point, we will define, of course, distance. When we will, yeah, let's actually let's look at the function first, then we will have better picture. Definitely domain all of the numbers. That's, we have to find a critical point, and we have to make sure that that extreme values, that local extreme values, is the absolute extreme. Okay, distance. That's the distance formula that everybody remembers. Yeah, I hope. And then we can do it for our point x minus 0, y minus 0. We, of course, don't need zeros. X squared minus y squared. And everything is perfect, but we have x and y. We need the distance in terms of one variable. I will replace y with 4x plus 7. 4x plus 7. Okay, I think this looks okay. That's the function that we have to find a minimum. The only thing is, looks a little bit maybe complicated with that square root. But what we can do, in order to minimize this square root, we know that we have to minimize the item inside. If the item inside, if the quantity inside is small, the square root of the small number is small. That's what I can do. I can maybe take a square root. I can square both sides. And instead of d, this looks weird, but my function will be called d squared, because it's enough to minimize this, yeah, to work just with this function. And if the quantity inside is minimum, then the square root of this quantity is also minimum. Yeah, I type this. Like, instead of minimizing the entire distance, the square root, we can just minimizing its square. That's the same thing. Okay, because now the function looks a little bit better. Yeah? And actually now we can think, because this is x squared, yeah, we can see, and 4x we will also square. It's quadratic function, x squared. Leading coefficient positive. That means now we can talk a little bit better. It's quadratic function. As x becomes bigger, because domain is all of the numbers, the values are going to the positive infinity. Yeah? And if we will find out critical point, this will be definitely a minimum, the lowest point. It means that lowest, locally lowest point is also the absolutely lowest point. That's what we're looking. Okay, let's find the x value that will minimize this function and the x value that will give us closest distance. Looking at the graph, I hope we're expecting a negative number. Probably a fraction, weird fraction, yes, but we're expecting a negative number. Let's see. We need domain, derivative. We need derivative. Let's differentiate. Derivative of our function is, derivative of x squared is 2x. Then derivative of quantity 4x plus 7 squared is 2 times 4x plus 7 times 4. 4 is derivative of the inner function. And when I distribute, I still didn't distribute, 2 and 4 is 8. And then 8 times 4, 32 plus 2, 38. 8 times 7, 56. That's the good derivative. Now, derivative is 0 if 34x plus 56 is 0. We can solve for x, and I just divided by 2. Now I think we have to leave it. But negative 28 over 17. We were expecting negative, and I think that number is somewhere here. Okay, what we can do, okay, I don't have a test. Negative 28 over 17, that's the critical point. Let's just check if this is definitely minimum. This is good derivative, okay. This prime, it's squared, but d prime. If I substitute 1, for instance, because 1 is greater than this, we will have positive, yes? 34 times 1 plus 56, positive, and we will get the number big negative. This will be negative. Okay, then our function, which is defined as a d squared, is decreasing, increasing, local minimum value. But we know that this local minimum is definitely absolute minimum, no lower points for that function, because this is, where is the function? This is quadratic function with the leading coefficient. It's going up. Yeah? And this is definitely, that means the x value is this, and the y value will be 4 times negative 28 over 17 plus 7. I'm not going to calculate this. It has to be positive number because that's the y. Okay, but negative 28 over 17, that's way too complicated number. Okay, that means this, the last question is actually the minimum. Yeah? Please, yeah, please even redo the same problems. Okay? Even redo the same problems. But doing your weekly assignments, you will have enough practice. Okay, thank you very much.